The tunnel boring machine, or TBM, is a powerful tool that helps us dig tunnels through different types of soil and rocks. However, TBM tunneling faces risks and challenges when encountering unexpected geological conditions. Limited information on site conditions is one of the major risks associated with TBM tunnel construction project. We recently developed the Smart Boring System, a TBM independent look-ahead solution that streamlines tunneling risks predictions by incorporating data acquisition, processing, interpretation, and reporting. To better understand this cutting-edge technology, we encourage you to watch our previous videos. These cover topics such as data acquisition using both geophone and DAS arrays, and validation of tunnel look-ahead results using TBM parameters. In this video, we will focus on one of the innovative technologies used in Smart Boring's data processing. Smart Boring is designed to deploy sensors and active sources inside the tunnel. This figure shows field data acquired by a 24 geophone array on one side of a TBM tunnel, filtered from 70 to 180 Hz. By picking the force arrival, we can estimate the surface wave velocity of the surrounding media. After removing the force arrival from the data, we can more clearly see the reflected events. Scanning the data with the picked force arrival velocity, we obtain a semblance curve. The peaks of this curve indicate potential seismic reflections ahead of the TBM. For example, the fourth peak might represent the reflection from the cutter head, while the following two peaks could be caused by reflections from geological changes located 10 meters and 29 meters ahead of the cutter head. Data can also be collected from the left-hand side wall of the tunnel. Due to the space limitations within the tunnel, the left-hand side array is positioned 8.4 meters behind the right-hand side array. The figure displays the left-hand side data filtered using the same frequency band as the right-hand side data. In the semblance curve, the fourth peak could again come from the TBM cutter head. Three other potential seismic reflections are detected at a distance of 10 meters, 26 meters, and 44 meters in front of the cutter head. Both right and left-hand side data consistently detected a reflection 10 meters ahead of the cutter head, increasing our confidence in an obstacle at that distance. However, seismic measurements show uncertainties in detecting the second and third reflections. Inconsistencies arise in the location of the second seismic reflection, and the absence of third reflection at 44 meters in the right-hand side data reduces the likelihood of an obstacle at that position. Seismic uncertainty can be caused by several facts, including improper assumption of a homogeneous media, limitation of the seismic resolution, which depends on the seismic wavelength and signal-to-noise ratio. In this case, the seismic wavelength ranges from 4 to 10 meters. Acquisition geometry aperture. Our numerical simulation shows a single-side array's detection aperture is about 10 degrees, meaning seismic method may struggle to pinpoint obstacles directly ahead or to the side if within this aperture. To mitigate the seismic uncertainty, we propose a new method to quantify the seismic observation use Bayesian Inference on multiple seismic data. Based on Bayesian Inference theory, given seismic observation date D, the probability of the existence of an interface at location Z can be calculated using the following formula. Here, Pz represents the prior probability of the existence of an interface at location Z without considering the seismic data. Pz given D denotes the likelihood of observing seismic data D, assuming there is an interface at location Z. Pd is the normalization function that ensures Pz given D is a proper distribution, meaning that the integral of Pz given D is equal to 1. Now, the key is determining how to define the prior probability and the likelihood in the case of tunnel look-ahead. Without any seismic data, the prior probability can be set as a constant number, such as 0.5, meaning there is an equal probability for the existence or non-existence of an interface. Alternatively, we can construct Pz using the borehole information to incorporate prior knowledge about the geological conditions in the area. For the likelihood, we can build it from the semblance curve. First, remove the reflections before the cut ahead. Then, implement a time-to-distance conversion. After that, normalize the curve by the area under each peak. We can then use the normalized semblance curve to represent the probability density. Following the same procedure, we can obtain the likelihood from the left-hand side data. Since the left and right side data are independent from each other, the prediction result from the right-hand side data can be considered as a prior probability for the left-hand side data processing. According to the Bayesian rule, the added observation of left-hand side data will change the posterior probability as shown in the formula. By multiplying the right and left-hand side data probability density functions, we got the joint posterior probability distribution. As shown in this example, Bayesian inference increases the first peak's probability due to data consistency, while it reduces the next two peaks' probabilities due to inconsistency. As the TBM moves forward, continuous observation are recommended. This means that multiple measurements will be taken for the same reflection. The final posterior probability can be calculated using this formula, where D1 to Dm represent the continuous seismic observations as the TBM advances. We apply the proposed Bayesian inference method to 11 continuous tunnel look-ahead experiments at a TBM tunneling site in Singapore. Each experiment consists of right-hand side and left-hand side observations. The site areas contains multiple soil and rock interfaces. The TBM progresses from right-hand side to left-hand side at a penetration rate of 6 rings per day, with 1 ring equal to 1.4 meters. During the half-an-hour acquisitions, the TBM's position shift is ignored. This video shows how probability distribution changes as more observations are added to the Bayesian inference process. The top figures present left and right-hand side measurements from each experiment, processed separately in low, medium, and high-frequency bands. The middle figure presents daily posterior probabilities with lines in different color representing tunnel look-ahead detection using data from individual experiments. The bottom figure displays the cumulative probability incorporating all observations up to the current acquisition. As more data is added, we detected 5 high peaks in the probability distribution, which could indicate a high likelihood of interface existence at these locations. The small peaks between rings 700 and 710 neither increase or cancel out as more data is added, suggesting high seismic uncertainty in this section. It is important to note that the Bayesian method provides a relatively quantitative description of the interface existence probability. However, determining an appropriate threshold for judgment remains a challenge and requires additional data and experience for calibration. To validate the Bayesian inference result, we compare them with cuttings density and borehole information. As seen in the top figure, there is good consistency between the 4 peaks on the right and the locations where density suddenly changes. They also align well with borehole information. The peak at ring 718 corresponds to the tunnel's termination point, where there is a strong impedance interface between rock and air. Beyond ring 700, the tunnel nears the underground subway station. Ground improvements in this area might increase the heterogeneity of the nearby geology, potentially leading to high seismic uncertainty. In conclusion, the proposed Bayesian method quantifies tunneling risks using continuous tunnel lookup data. When multiple data are consistent, there is a higher certainty in detecting obstructions. Bayesian Inference offers a framework for interrogating all datasets and prior information. The prior information can include not only interpreted geology, but also density values or modulus of core samples. In closing, I'd like to thank LTA and Cambridge Sensing for their support in this research. If you have any questions, please feel free to contact me. You can also learn more about our work through our website, YouTube, or Bilibili channels. Thank you for watching.